Okay, so what we're going to do now is from now on, I'm going to break down the lectures to smaller chunks, makes them easier for you to watch, and I'll upload them. So we get to lecture 9 this time. And what we're going to do is we're going to look at an idea of what we call bounding probabilities. So let's imagine we have a scenario where we're trying to model a real-world situation and we don't know one of the named distributions. So far we've covered Bernoulli, binomial, geometric, and Poisson. But let's say we're looking at some process and we don't know the true distribution, or we don't know which one to use. Now, what the bounding probabilities will do is it will give us a way of at least having a lower or upper bound on the probability of certain things. So it won't give us the exact probability mass function. We can't get the exact information, but at least we can get some bounds for it. And we're going to look at a couple. We're going to start with the tail sum formula, which is in this video. And then the next one we'll do Markov's inequality, and finally we'll do Chebyshev's. So let's start with what we call the tail sum formula. So y in this case is a discrete random variable that takes the values. Now notice the values are 0 up to n. We don't have any negative values. That's not how we're setting this up. We are just assuming that it has the value 0, and I'm going to bound it at this point at n. I can rewrite the expected value in terms of a load of greater than calculations. So, and this will come in useful for actually a sort of, I think this is a lemma. It's going to be a starting point we're going to use in some of the other theorems later. So we do have a proof here, but let me go through it slowly since we've got some time. So let's set this up, get some color, and let's look at what we've got here. So we're looking at the expected value of x. And what is that? That is, well, by definition, we'll put k. This is k from, we know the values are 0 up to n. K times the probability that x equals k. Well, we know that it takes the value 0, 1, 2, 3. So let's write this out a bit longer. So we've got 0 times the probability that x equals 0 plus 1 times the probability that x equals 1 plus 2 times the probability x equals 2 plus dot 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 plus all the way n times the probability that x equals n. Okay. I'm going to really go old school and write this long form. So 0 times, that's just going to be 0. No problem. The first one, we've got the probability that x equals 1. Plus, well, I've got 2 times this. I'm going to write it twice. I've got the probability that x equals 2 plus the probability that x equals 2 plus, well, the third one, I've got the probability that x equals 3 plus the probability that x equals 3 plus the probability that x equals 3 plus dot 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 plus we've got the probability that x equals n plus the probability that x equals n plus I'm going to go all the way over here to the probability that x equals n. In fact, that final line, this will be n times. Well, look at this. What's this first column here? This column here is the probability that x is greater than or equal to 1, because I've got the probability that x equals 1, then 2, then 3, all the way up to n. So that's good. What about this next column? Well, this is the probability that x is greater than or equal to 2. And then this next column will be the probability that x is greater than or equal to 3. All the way to the last one, all I've got is the probability that x is greater than or equal to n, which is just x equals n. So if we now put this back together, what do we actually get? we have the probability that x is greater than or equal to 1 plus, because the thing about plus is I can rearrange the order. That's not a problem. The probability that x is greater than or equal to 2 plus the probability that x is greater than or equal to 3 plus dot 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 plus the probability that x is greater than or equal to n, which if you now write back in the summation notation is going to be I from 1 to n probability that x is greater than or equal to I, which is what we had there. So that's our tail sum, our tail sum formula. Next time we will go in and we will start with the Markov inequality. See you next time.